Hi everyone, welcome. We're very happy to have Jamie Sikora here today. Jamie got his Ph.D. at Waterloo and has done postdocs in Paris,
Singapore.
I was going to get the order. I was trying to get the order right. Paris, Singapore, and is now at the world-renowned Perimeter Institute. It's like the Perimeter Institute for
Theoretical Physics.
Yeah, he's going to tell us some about this. And I also wanted to add that he is literally writing the book on semi-definite programming and quantum theory. So you can ask him about that later if he doesn't mention some of it in his talk. So please join me in welcoming Jamie.
Thank you. Good. Thank you very much for the nice introduction. And of course, thank you all for coming. I know this is not the typical time to have this seminar, so I appreciate everyone sharing your Thursday or Tuesday with me. I'm going to be talking about quantum resources. Okay, so I'm guessing not everyone here studies quantum a lot. So anyway, it's going to be a very gentle introduction to quantum. Okay, I'm going to avoid all the funny notation, all these technical things. I'm going to really talk with my hands through the quantum parts. Okay, that being said, if there's any questions, do feel free just to shout out. And this is work in progress as well. So we're writing it up now, but if you have any ideas or anything like that, please let me know. Any strong feelings. I'm very happy to hear all these things. Okay? And what I'm going to be talking about as well is a tool that can be used in quantum theory, but it doesn't have to be used in quantum theory. So if anyone has any ideas, maybe relating it to their own research or something, I'm always very happy to hear about this. Okay, so quantum resources. What are they and how much are they worth? So here's the plan. I'm going to spend the first half of the talk, maybe not quite half, but chunk of the talk, talking about an economist's viewpoint on optimization problems, okay? And how to assign values to resources. So this is going to be, that's probably fine. So this is going to be a mathematical tool, okay? I'm going to just talk about it, develop some theory, and then I'm going to apply it to quantum. So the quantum things I'm going to apply to is quantum physics, so building a quantum computer, updating quantum hardware, learning quantum states and why I think it's cool, and hopefully I'll convince you that it's also cool. Creating quantum entanglement, so that's cool. There's a couple of buzzwords there. And distance measures, okay? And this is joint work with Gary Au, okay, at the University of Saskatchewan. So here's the overall theme of the talk. So we have quantum, we have economics, okay? So quantum is like a billion-dollar industry right now, okay? People are spending tons of money. It's not generating billions of dollars right now, but people are spending tons of money on it, okay? So economics is the theory of, spending money, right? So we're basically going to be looking at, making wise economics decisions when it comes to quantum, okay? That's kind of like the theme anyway. So here's real life before I start talking about quantum stuff. Well, quantum's real, but there's a real life application. Here's an employee, there's a boss, and this is a real job. So I just solved the computation you asked me for. Like you could imagine it took 2 months to solve, some really big computation. And the boss is like, that's great, but in the last 2 months, some of the data has changed. Okay, so the employee said, because just wasted all this computation time. The question is, do we have to do this computation again? Okay. And of course, the answer depends on what computation was ran and what the boss wants from the computation. So you might have to, you may not. Okay? So this is going to be something we're going to look at. And of course, these things happen all the time. So imagine if you work for an airline company, you're dealing with thousands of employees. Okay? You're dealing with hundreds of planes, and there's certain constraints that you need. Okay, so you can solve for the best way to allocate all your resources. And there's constraints, like one person cannot work for 200 hours in a row. Okay, even though you think that would be optimal, it's just not feasible. It's not going to work. You need airplanes on the tarmac at the right spots at the right time, all this stuff. So there's lots of moving parts. You could solve these things, but it could take a long time. Why do you do it? Well, you're going to save the company a lot of money. But things happen in real time in the real world, okay? So you just can't sit for 2 months and just solve something, right? So we're going to look at what kind of computations need to be redone or what doesn't have to be redone. So here's a small thing. So this is resource management up there. It's kind of hard to read. So here's a factory, and they're just going to make two commodities, two things, orange juice and apple juice. Okay? So orange juice brings in $3 per unit, and apple juice brings in $4. I just totally made up these numbers, so don't read too much into it. But the question is, how much orange juice and apple juice should you make? Well, for everything I've told you so far, you should just make an infinite amount of juice, because then you have an infinite amount of money and life would be swell. But you can't make an infinite amount of juice. It doesn't make any sense. Because it's resources. There's water, there's fruit, electricity, staff and labor. All these things go into making, juice. But what you can do is, given a set amount of resources, you can solve for the best way to produce the juice that you'll make the most amount of money. Okay? So this is called a linear program. It's a very particular kind of optimization. And what we're going to do is let x and y be the amount of orange juice you make and apple juice. Okay? And these are non-negative because we're only going to make a non-negative amount of juice. And this was the formula that I had before, 3x plus 4y. This is the amount of money you'll bring in. But what constrains you from making an infinite amount of juice are the resources. So right here, so these numbers don't really mean anything, I just threw them in there. But this 3 here, suppose you have 3 units of electricity, okay? Or 5 units of water, 6 units of fruit, and 6 units of labor, 6 people working. It's okay, so there's inequalities here. It's okay if you don't use all the resources. If you're not gonna make that much, if you're not gonna make an optimal amount of money, then it's okay not to use the resources, but you can use more than what you have, okay? So you can solve this, and you can find out the optimal production plan, okay? But suppose you did this. Suppose it took a long time to solve. Some of the information changed a little bit. So here's the big question. It's going to kind of motivate this line of work. How much would you pay for more labor? Okay? Or how much would you pay for more water? Or whatever. So there's 3 cases just to get us thinking about it. One, it's very valuable. Okay? So labor was a bottleneck in your production. So if you were to get more labor, you would make more money. Okay, plain and simple. 1, it's not valuable. You're not using all that you have. Okay, suppose you already have an optimal production plan, but you have people in the back playing checkers. You're just not using them all. So you would not be, there's no incentive to hire more people. And 3 is the boundary case. You're using all that you have. Okay, so no one's playing checkers. But if you had more people come join your company, they would have nothing to do. Okay? So that's kind of like the boundary case. So here's a solution. You could just put a +1 here for 1 more unit of labor, whatever that may be. And you could solve it again. Okay? Well, if you want 2 more, you could solve it again, and so on and so forth. But remember, these things could take a very long time to solve. Okay? So maybe you don't want to keep solving these things. So here's a softer question that I'm going to ask. What about the instantaneous change in profit? Okay, so as you start getting a little bit more labor, okay, let's say hours of labor, okay, what is the instantaneous change in the profit? Okay, so this is called the shadow price. Okay, so this is the shadow price of labor. Okay, so let's go back to our example. So here's a wholesaler. And the wholesaler is going to offer the juice company some kind of deal. Okay? He's going to say, I'll sell you $3 per unit of water. And the question is, should you accept it or should you not accept it? It's really a yes, no answer. You either buy it or you don't. So the question is, should you buy any water? And the shadow price is the maximum price at which the boss will say yes. Okay? So imagine if it's really, really cheap, okay, and you'll make more money, then you'd want to buy it. If it's really, really expensive, you would not buy it. Okay? So at some point, the answer is going to switch from yes to no. And that is going to be the shadow price. Okay? We can also talk about selling resources. I'm not going to go into detail in this talk, but if you're interested, please come talk to me. Right, so what we're going to do now, So far, I've wrote up a linear program, and I said, okay, this is what it looks like in the real world. Should you buy more labor, whatever. I'm going to introduce a little bit of math now. So this is a general linear program. Many of you have probably seen one before. So right here, x is going to be some fixed size vector, non-negative entries. Okay, so you could have as many entries as you want. You could have apple juice, orange juice, grapefruit juice, whatever. This is some linear function, so you could think of it as profit. And there's all these constraints, whatever they may be. Okay, this doesn't pertain to orange juice. This is not the mathematical theory of orange juice. This can be modeled many, many problems. Okay? So now, with linear programming, there's this thing called duality theory. Okay? So I'm going to introduce a little bit of math just to see where the shadow prices come from. So each constraint is going to have a dual variable. Okay? You can think of them as Lagrange multipliers if you want. Okay? But in general, I'm just going to call them dual variables. And there's this thing called a dual program. And throughout my talk, every time I show you a dual problem, I'm going to just show you this magic wand because I'm not going to tell you where it came from or how I got it. Okay? It's just going to appear like magic. If you're interested, please come talk to me. I'm very happy to show you, but it's just magic, okay? So the dual program is going to look like this. You're going to minimize this sum biyi. Okay, so the b's are on the constraints. They're going to go upstairs. These a's kind of stay where they are, and the c is upstairs here, the thing you want to maximize, and now it's coming down into the constraint. Okay, so that's called a dual program. Notice there's no x's involved. What I've done is I said, hey, here's a bunch of dual variables. Here's a new optimization problem. And that's it. I've just defined it. Okay? Now, there's lots of reasons to look at this optimization problem, but I'm going to have one very particular reason. So suppose you had an optimal solution to this dual program. Okay? The shadow price for each resource is given by the optimal dual solution. Okay? So you have y1 to ym star. So you solve it, and let's say I want the shadow price for B2, which is some kind of resource. Y2 star is going to tell you that shadow price. Okay? And the instantaneous change of profit is this yi star times epsilon. Okay? So as you start buying more of resource I, this is the amount of money you're going to see. Okay? And you can look at like you have some kind of big Groupon. So if someone's offering you, this much more resource 1, this much more resource 2, you can calculate what your change in profit up here as you get all these resources. Okay, so it's like some bundle deal. And it's pretty much the simplest thing you could imagine. It's just this linear combination of the dual variables and how much more each one is offering, these epsilon i's. Okay. And there's going to be some issue. What if there's more than one dual solution? Then we minimize. But that's just a technical thing. Just suppose you have an optimal dual solution. Okay? And they give you the shadow price. Okay? And the nice thing is whenever you solve these linear programs, let's say in practice or for research or whatever, the dual variable is something you're given for free almost all the time. Okay? So the shadow price is free information. Okay? If you don't care about how these resources change or whatever, you just want to solve and move on, that's totally fine. But if you care about how your profit changes as you move things around, then this is free information. Okay? Okay, so I keep talking about rates of change and stuff like that. So if you want to get technical, it's really just a directional derivative. Okay? So here's a nice function. This is a function of b. And you solve this optimization problem. Okay? So you have b1 up to bm. Okay? So what this function does is say, here is, let's say, a basket. Here's a basket of resources, so much water, so much fruit, whatever. This function is going to output the maximum amount of money you can make with these resources. Okay? So it's a very nice, well-defined function. And you can look at how the function changes in the direction of t. And you just look at the dual optimal solution. And you take the inner product with t. Okay? So this y star is given to you for free. So it's just a very simple inner product that you can compute. Okay? Any questions at this point? It's not going to get, this is the technical part, and once it's done, I'm just going to sweep it all under the carpet anyway. So if there's any questions, feel free to shout. Okay. Okay, so that was something that was known. If you look up shadow prices, you can find this stuff. What I needed was a matrix variable. Okay, so I'm going to generalize this linear program to something called a semi-definite program. And what this is, it's a maximization over a matrix variable now. Why do I want a matrix variable? Well, when I go to quantum eventually, everything basically involves matrices. Okay, so I needed to kind of upgrade that previous theorem. So this means X is positive semi-definite, so it has non-negative eigenvalues. Okay, before I had non-negative vectors, but the right notion of non-negativity for matrices is usually bounding the eigenvalues, okay? At least when it comes to quantum theory, okay? This is going to be some super operator. So you input a matrix, it's going to output another matrix. And this has to be less than or equal to B, which means that B minus this thing is non-negative eigenvalues, okay? And this inner product Cx is just the trace of C times X. So this is called the Hilbert-Schmidt inner product, okay? So if you're comfortable with the linear program, then all I'm doing is making the variable into a matrix now. Okay? And basically everything else conceptually is the same.
I'm just wondering a little more about what is like capital phi, like what's a super operator?
So the super operator can be anything. It has to be linear. You're going to input a Hermitian matrix. I'm going to need complex values for quantum theory. It's a matrix. And it's going to output another Hermitian matrix. But that's it. It could be a different size. So the simplest one is just the trace. The trace is a nice super operator. Yeah, or you could just add something to it if you want. It could be very simple. Yeah. Any other questions? So let's jump to the matrix thing. Yeah.
Just to confirm, the super operator would be a linear operator, right? So you can still write it as a trace inner product of some matrices. But it's
That's right.
a lot of trace inner products.
That's right. That's right. Exactly. Yeah. So another way to write this, you could just have a bunch of trace inner products, and then, well, let's suppose this was equal to B, just for simplicity. It'd be a bunch of trace inner products equal to B. Just like if you do this for linear programming, then that extends naturally. Yeah. I'm not actually going to do too much with these semi-definite programs other than show them and point to them and keep saying they're interesting, but I'm not actually going to do much math with them, so it's totally okay. So we had to extend what was known for linear programming to semi-definite programming, so we could apply it to quantum theory. There's a line here. It's just some mumbo jumbo. Don't worry about it. But this function is the same one we had for linear programming. Okay. So this is just some math just to make it work. It's whenever you go to matrix variables, you need this extra math. But right here, you have some B here. So it's a matrix. So it's kind of hard to think of it as some allotment of resources now. But it's still just some matrix. You plug it in, and you get some value, okay, whatever that value may be. Okay. Then you can look at the directional derivative as you change this B here. Okay. I'm going to start calling it shadow price. I don't want to keep saying directional derivative, especially in a computer science program. I'm not sure how people feel about calculus. But this was really neat, too, because semi-definite programming is something I look at every day. It's like my favorite thing to do in research. And then I found a way to differentiate, for free. So I thought that was really cool. Right, so now we can look at how things change as B changes. So let's come back to the real life example before I get to quantum. Do we have to do the computation again? So here's an example of some time where you don't. The boss says, well, the data did change. Now what I really want to know is whether I should buy more water at $3 per unit, because that was the deal the wholesaler gave. So the employee goes back to the person who solved the problem and said, well, what I really want to know is whether I should buy this water. The employee looks up the dual variable, which he had for free. Didn't know he was going to need it, but it was just laying around. And then says, well, the shadow price is $2. Okay, so you'd lose money if you did that. If it costs $3, but you're only going to start making $2 from it, then you should not do it. Okay? So you could answer the question, no, you should not buy the water. Okay? And let's see. Okay, so before I get to quantum theory, shadow prices are, this is concept in economics. And what it does in a nutshell is it assigns some value to something that doesn't have a market value. Okay? So if I'm running a company and you're running a company, how much a resource is worth to me is going to be different to how much it's worth to you. Okay? And it also depends on how I'm running the company. Okay? So it's really like right now for this person, how much is something worth to them? That's what shadow pricing does. They can also help answer difficult or awkward questions. Here's an awkward question. Should a company spend X dollars a year to save Y tons of carbon emissions? Okay? Now, of course, you should invest as much money to reduce carbon emissions as much as possible because no one likes to breathe poison, right? But if you're a small company, maybe you're worth, $1 million, you don't want to spend $10 million just to save carbon emissions. Well, that makes no sense. But if you're a big company like Microsoft or Google or something, maybe they do want that good public image or something. Okay, so maybe they will spend millions of dollars to reduce carbon emissions. Okay. Here's an even more awkward question. Should the government spend X dollars to build safer roads which will save Y lives per year? Okay. Now, what's the value of a human life? It's infinity dollars, right? But, no government has an infinite amount of money to spend, right? So we live in a world with limited resources, and you have to make the best decisions on how to spend those resources, okay? So that's where shadow pricing can come in handy, okay? So I'm going to move on to quantum. I think there's some time for questions. Any questions about shadow pricing? Any? Yep.
You said you get the shadow price for free?
Yeah.
So you have a linear program, you solve it, you have a solution, how do you compute the shadow price from the solution?
Right, so usually the way algorithms work is they give you a dual solution for free, and this dual solution will kind of certify the optimality of your solution.
Okay. Are there
Okay.
situations where like the dual and the original problem don't have the same, like there's a gap or something?
So for a linear program, if you solve the original problem, and you solve the dual problem, they'll always be equal, assuming they're both finite, say. For a semi-definite program, it's not the case. And there was a line there that I said, don't worry about. That's what that line says. That line says that they're equal. Yeah. Question? Yeah.
So let's say you calculate your shadow prices and then you decide to buy more water.
Mm-hmm.
And then they come back and they say, okay, well, we also have labor. Like after you decide to buy more water, what do you have to rerun your calculation of that?
Yeah, so what this does, I keep mentioning these derivatives. What it's doing is giving you some kind of linear approximation to your optimal solution. So even if you have any kind of function and you have some linear approximation, you start taking advantage of it. So you start moving around. Now you're losing all that information that you had. So it's really like the instantaneous change. For a linear program, this is nice though, because usually there's some positive amount that you can actually move in that direction. So this linear approximation is actually going to be an exact approximation. We don't know for how long, but for a little while. Yeah. Any more questions? Mm-hmm.
Is it always a lower bound?
So if there's optimal solutions, then you're supposed to maximize or minimize over these dual solutions. But if someone just gives you one, say from an algorithm, this will give you a bound on the shadow price. Was that what you meant by lower bound, or?
I meant just to follow up on Jesse's question. Like,
It's probably, I think you can construct cases where it's not. But it could be. I'd have to think about it. That's a very bad answer. But yeah.
I mean, if you're taking a convex function and linearizing,
That's what I was thinking of as
then
convex.
the linear function is always the lower bound of the convex function.
Yeah, this function f of b is going to be convex, so I think it will be a lower bound. Whether it's kind of like a supporting lower bound, I'm not sure. It's probably, yeah. Any other questions before going to quantum? Okay, so now what I'm going to do is introduce a handful of quantum problems, depending on how much time I have. And each one I'm going to write as an optimization problem, okay? So simulating quantum systems / building a quantum computer, okay? Right. So here's a snapshot of modern physics. make things really, really cold and see what happens. Okay? Of course, this doesn't do physics justice, but there's some truth in that. Okay? So here's some neat things that happen whenever physicists start making things cold. So this is helium. Helium is usually not a liquid. Okay? But if you freeze it down to 4K, which is really cold, it'll turn liquid. And if you freeze it a little bit more to 2.17 Kelvin, then it turns into a superfluid. What's a superfluid? Well, it's a fluid that has 0 viscosity, like hard 0. Okay? So you have this bowl, it's a superfluid. You'll see the liquid starts creeping up the sides, going around the corners, and dripping down the bottom here. It's a little wee drop there. It's kind of hard to see. Okay? So neat things are happening. If, let's say, instead of helium, you just make some metals really, really cold, now they'll turn superconducting. Superconducting means the metal has 0 resistance. Okay? So this thing is going to start rejecting changes in magnetic field. Okay? So this is a fun thing I like to do at summer camps, so high school students. Just freeze it. Usually I don't get down to 40 K. Usually I use like liquid nitrogen, something like that. And then you'll have a track here with magnets. And this thing will just levitate. Okay? And since there's 0 resistance, you just give it a flick, and it'll just keep zipping around. Okay? It's really cool. But what's neat is if you take this track, while it's zipping around, you turn it upside down, it'll just keep zipping around. Okay? Because it's rejecting the changes in magnetic field, so it doesn't want to get close, so it doesn't want to move farther away either. Okay? This is something really neat to show people. So, you know, science fairs and stuff, it's interesting, but we want to build quantum computers. Okay? So this is a 4-qubit chip from IBM. Okay? They have a lot more qubits now, but this is from a couple years ago. And whenever you make metal superconducting and you have this computer chip, neat things will happen. Okay? And by neat things, I mean now you can build quantum bits or quantum qubits. Okay? Qubits are kind of neat. But what we're going to do is we're going to look at the physics behind it just for a little bit, then I'm going to translate into math. So if you have a physics experiment, let's say a quantum computer, okay, the interactions of the physics are governed by a thing called a Hamiltonian. A Hamiltonian is just some really, really big Hermitian matrix. Okay? And at very low temperatures, this quantum system is going to go into its ground state, like the liquid helium or the superconducting, the places where neat things happen. Okay? And the ground state is just the eigenspace corresponding to its smallest eigenvalue. Okay? So it could be degenerate, there could be lots of eigenvectors in that eigenspace, but nonetheless, it's a nice eigenspace. Okay? So that's great. What I care about for the optimization is I wanted to compute what's called its ground energy. Okay? So the ground energy is just going to be the smallest eigenvalue of the Hamiltonian. Okay? So one way to compute a smallest eigenvalue, okay, is to solve this semi-definite program. You want to maximize lambda such that lambda identity is less than h. Okay? And lambda, I'm saying is non-negative, doesn't really matter. But this will give you the smallest eigenvalue. And this Hamiltonian, this h here, is very, very large. Okay? For each qubit you have, if you have n qubits, this h will be 2 to the n by 2 to the n. So it's growing exponential. So if you solve this SDP, or this optimization, you probably only want to do it once. What if we perturb the Hamiltonian? Okay? I want to change this Hermitian matrix. Why do you want to do that? Well, if you have some quantum experiment, okay, quantum computer or whatever, you probably want to do something with it, right? If you just have a computer and you're not doing anything, it's not computing anything. So we're going to change this Hamiltonian towards a different direction, h prime. Okay? So you could like shoot lasers at it, microwave pulses, change the magnetic field, all these really cool physics terms, they apply here. Okay? So you're going to change what's happening. Okay? And this is what's happening inside a quantum computer. You have some state, and then you say, oh, well, what I want to do is factor, or I want to do this or that. So you have to change things around, and that's going to do the computation. So I want to know the shadow price of this. So here's the magic wand. I'm going to define the dual. The dual looks like this. Minimize y in a product with h. The trace of y has to be larger or equal to 1, and it has to be plus semi-definite. Okay, so I'm not going to explain where that came from. I'm happy to chat about it later if anyone's interested. So this dual is great. And from that, if you solve it, you'll get an optimal y star, okay, right here. And you just take the inner product with h prime. And h prime was the direction you wanted to move. Okay? So this gives you the shadow energy. Okay? I'm not talking about money anymore. I'm talking about what's happening inside this quantum computer. Okay? So that's the shadow energy. And we can continue doing this. We can compute the second smallest eigenvalue, the third smallest eigenvalue. And you'll get a whole spectrum of eigenvalues. Okay? Physicists like to write them like this. Okay? So here's the smallest one. There's the largest one. There's going to be possibly exponentially many. But one thing we care about in at least some quantum experiments is this, what's called the spectral gap. Okay? We want the gap to be large. If it's small, your computation could just get thrown off. So we have a spectral gap. But we have a handle now on the shadow energies. Okay? So right here, if the second smallest one is decreasing at a large rate, and the smallest one's increasing, then if you were to move in that direction, or let's say do that thing in the quantum computer, that would be bad. It'll throw off your computation. Okay? This would be good. It's preserving the gap. And this is okay. You know, it's not increasing it, but it's preserving it. Okay? And again, this is free information. So if you go ahead and calculate those energies, you'll get for free whether or not you should move in this direction. Mm-hmm.
So again, follow why having this gap between the first and the second eigenvalue is good, but then you don't care about the rest. Because I see a small gap in other.
Right.
Go up.
Right. So I didn't say. So you have to trust me, but there's some kind of computations that require this to be large. And the reason is you're going to encode information in these eigenvalues. Okay? I think it's actually encoded into the smallest one. And as you do your computation, you want it to go in a certain path. And then at the very end, this eigenvalue is going to give you your answer. Let's say you're factoring something. Let's say the factor is this. Okay? If these ever cross, it's just going to mess everything up, and it will not go on that nice path that I described. It's not obvious at all what I'm saying, but that's the answer. Yeah. Mm-hmm.
I'm a little confused. Why would you need to write a semi-definite program to calculate something like an eigenvalue?
You don't need to, but if you did. So this is kind of a warm-up example,
Oh.
I admit, yeah. But again, these are exponentially large.
Oh.
So, you know, you might want to. There's probably better algorithms that just go directly to it. There's actually quantum algorithms that'll do it as well, but yeah. Yeah. Any more questions? Oh, I should say, if there's any questions, just feel free to shout out. Also, I'm going to be switching my applications quite rapidly. So if something I start saying doesn't make any sense to you at all, and you don't want to ask questions, just hang on for a few minutes. I'll probably talk about something else. Okay, so you can jump right back in. Like right now. So this is the second example. How much does it cost to update noisy quantum hardware? Okay, so this is a D-Wave machine. This is a Canadian company that's been making quantum computers for some time now. And we want to know whether they want to spend this funny Canadian money to build a larger one, a better one. Okay. So the question is, what's inside this thing? Okay. The answer is no one knows, which is a bit of a joke we use. Whenever you bought one of these things, they used to, I don't know how much they are now, but they used to be $10 million. Okay. And if you bought one, they would make you sign a contract saying you're not going to open this up to see what's inside. Okay. And this thing's big. This is like old school computers, like it'll fill a room. Okay. But you're not allowed opening it up. But you know, from a theoretical standpoint, I know what's inside. Just some quantum operation. Okay, phi here. Or at least that's what they want to be inside. This is what they want. This is what they're trying to build. Of course, we don't have these very good quantum computers yet. So we don't have the ideal thing. Okay, what we have is a noisy version of it. Okay. So the question is, how much would you pay for a better quantum computer, a better quantum process? Okay. So we're at some particular point, and we want to upgrade it to a better one. So here's some of this funny quantum notation. I'm not going to use it at all, but I'll just kind of point to it and I'll say what it means. So this is going to calculate the worst case probability of error. If you give it some x, this is the probability that it's going to say an incorrect value. Say, suppose I wanted to factor some large composite number. This is the probability that's going to give you the wrong number. Okay? So the input is x. So this is some of the funny quantum notation I was telling you about. Okay? So you stick it into your quantum computer, and this inner product is the probability that you get an incorrect answer. And this is some funny norm. It's called the diamond norm. And this is a norm on superoperators. Okay? And what I'm going to do is bounded by delta, and delta is going to be the noise. Okay? So if you're trying to build a quantum computer, your worst enemy is noise. Okay? In one word, you want to reduce noise. And this is very, very, very hard. Okay? But suppose we want to get a handle on how the quantum computation will work. Whenever you do decrease it, it's going to look like that. So this is what you want to happen. And you're in some kind of norm ball around it. If this norm ball is small, then you're going to be very, very close to what you really want, the ideal setting. Okay? But let's say if it's not that small, you could be far away. Okay? So the question is, how much does it increase or decrease as you decrease the noise? And this is not a semi-definite program the way I've written it, but you can just turn it into one. Okay? You look into a paper and you find out how to deal with this norm, basically. And this.
What did you say M was?
Sorry, where am I looking?
M in the max size.
Oh, okay. So this M here is a measurement.
Okay.
So you have a quantum state. It's wherever. This M here is going to be a measurement, and f of x is the outcome of the measurement. So you're just going to measure, and it's going to spit out f of x. And this identity minus is that, so with this is the probability being correct, and identity minus is probability being incorrect. Why do I worry about that? Well, I want it to be a maximization problem, because that's the theorem I developed. Yeah. Mm-hmm.
How do you fix x?
That's a very good question. So this is not the way everyone would want to calculate whether or not they should upgrade their quantum computer. This is just some kind of simplified snapshot. So what I would do here, so x is a particular input. So what I would do is probably just take some random sample. So if you take some random sample, do it uniformly at random, then this will give you a bound on error for that. And hopefully that would be a good representation. Yeah, but that's a very good question.
So I have a question.
Mm-hmm.
Do you know phi prime? Because phi is the ideal one. Yeah.
You know phi right here. This is what you want it to do. Phi prime can be is anything your quantum computer could do being bounded. So phi prime is oh, sorry, there should be a little prime here. Just notice that. But phi prime is the variable here. Yeah. And this is not saying this is exactly what your quantum computer is doing, but it's saying if this is the bound on the noise, this is what it could be doing with no other information. Yeah. Mm-hmm.
Just to follow up on Saran's question.
Yeah.
You are going to be sampling X, right? You're not just going to be.
You could. Right now, this is this could be for a single x, and this will give you a value for that single x, but it may not be a good representative. So you could just do a random sample if you want, and then this will be a nice linear function on upstairs as well, and you can still solve that as well. Of course, there's going to be many inputs, so you probably don't want to do them all. There's nothing stopping you, I guess, from doing them all, if you could calculate that inner product. But yeah. Mm-hmm.
How hard is that diamond norm to compute?
You can do it efficiently. And it was just shown, so the diamond norm, it also goes by other, if you look at operator algebras. It's also called the completely bounded norm. And it was just shown maybe 2012-ish that you can write it as a semi-definite program, and therefore you can compute it quickly. Oh, maybe I should have mentioned that. These semi-definite programs, you can compute them in polynomial time in the size of the matrix. Yeah.
And how big is the metric?
How big is the matrix?
Yeah.
Usually they're going to be exponentially large.
Can you give me a number?
Give you a number?
Yeah.
5? Every number is exponentially large. Okay, so
Because you need to solve that, correct?
if you want to solve it and you want to use a off-the-shelf STP solver, you're probably going to be bounded maybe to 1,000 by 1,000 matrix variable. Maybe it's a little bit better nowadays. It's probably less than 10,000 by 10,000. So yeah,
Not that.
it's not that big, but these solvers will take a long time. So right now, I'm more concerned about a computation that takes a long time that you don't want to solve again.
Yeah, I see. You don't solve
Yeah. Yeah. So this also depends on, the algorithm you're using and all this stuff. So some will be fast, some will be slow, but that's a good question. Mm-hmm.
Thanks for taking all these questions.
Yeah, of course.
So I guess I would actually be given like a quantum circuit, and then I could write down this huge matrix from it if I wanted to. Is that the way they would
Yeah.
actually be given to me?
Right. So this superoperator will be given to. There's lots of ways to represent a superoperator, but usually it's like a collection of matrices or one big matrix that's going to encompass them all. How you write a superoperator is a very interesting question.
Yeah, and I'm especially curious because if I'm given the superoperator in a very compact form, like just some small circuit, I'm wondering if you can solve semi-definite programs without having to write down, expand it out into a huge.
If it's given by a small circuit,
Or something small.
you mean like some kind of succinct representation
Yeah.
or something? Yeah, there might be some kind of shortcuts. Also, semi-definite programming is a way to compute these things, but I'm not going to say it's always the best. So if your data is given to you in a particular structured way, you may want to use a particular structure algorithm. But this is just one big hammer that seems to work on almost every quantum problem. So all I'm doing is swinging the hammer around. Yeah. Any more questions?
May I ask another?
Yeah, of course.
So this supercomputer is supposed to do what exactly? I mean, you come with this pi, but then it's only supposed to do some matrix manipulation. I mean, what is the role of this computer? I mean, you came with this pi. I mean,
Okay. So let's kind of parse what you're saying. So you have a quantum computer, and what I'm doing now is using a classical computer to solve this STP. And this STP is going to tell you how good the quantum computer is operating.
okay, and this pi is coming from somewhere. Somebody give that to you.
Yeah. So what you could do is crack open a quantum textbook and say, this is what Shor's factoring algorithm looks like. And then you could just do the math. You can compute what this is. And then this delta is going to be very large, probably, because we don't really have quantum computers to factor yet. At least I don't. Maybe some secret government lab does. But
But maybe it's a similar question. So
Yep.
kind of the question could be like, if I'm able to write down phi, does it mean that I can just simulate the quantum computer and I don't actually need it?
No. What you're doing is you're calculating an error.
Okay.
Yeah. So you have a quantum computer, and you're calculating the probability that's going to make an error. You're not simulating it, definitely. You can simulate a quantum computer if you have exponential classical time. But that's not what I'm doing.
But these are also exponentially large, so. Yeah.
Right. If you wanted to, yeah. But again, these are not good quantum computers. So simulating them is probably not something you want to do. But this is a big problem. Like whenever people come to the newspaper and say, I have a quantum computer, you always have a bunch of people saying, it's not doing anything quantum. Here's a classical algorithm that does it. But this is a big tug of war. Yeah. Okay, so maybe I'll move along. Oh yeah, so this is what a quantum computer actually looks like. It's a little bit blurry with this resolution, but it'll be just like this little wee chip, like a computer chip. And you have all these things that's going to do something to that chip. And then you put this little machine, so it'll be like this, and you put it into a huge vacuum. So it gets like 4 Kelvin or 10 to the Kelvin. Okay, learning quantum states. So Suppose Alice has a basket of quantum states. She's going to close her eyes, choose one at random, pick it out, and send it to Bob. Okay? Maybe through quantum email or whatever. Bob now is holding this quantum state, and he wants to learn what state he has. Okay? And the thing about quantum states, like you can hold them, not really, but you can have one, but you can't look at what it is. Okay? It's not like a piece of paper where it's just written down. If you look at it and you try to infer any information, it's going to collapse. It's going to fall apart. Okay? And there's different ways of looking at it. Okay? So this is called a measurement. Okay? So what Bob wants to do is perform the best measurement, or the best way of looking at the state to infer what he has. Okay? So why do people care about this problem? Okay? So building quantum computers, you can more or less trust me, people are interested. Why do people care about this? Well, you have a baby quantum machine learning problem. Okay? So you have some state, it could encode information. So there's this whole branch called quantum information. You could have some information encoded in the quantum state. You send it to your quantum computer, and you want your, well, depending on whose team you're on, you may or may not want the quantum computer to learn what the state is. Okay? There's cryptography. So you could buy these machines. This is an ID Quantique from Switzerland. They used to cost about 100K. I don't know how much they are now. But anyway, if you buy them, you can send secret messages to each other. Okay? So depending on who you are, you may or may not want to learn the quantum states. If you're Bob, the person who's supposed to receive the message, you may want them to be able to learn what's happening. If you're an eavesdropper, you may want them to not learn what's happening. So being able to learn or not learn could be good or bad depending on context. Cryptography. You start sending secret messages, and there's Alice. Here's an online quantum casino. You don't want the casino to be able to learn too much information about what's happening, or else maybe they could, get extra money from you, cheat you out of your money. So this is one of my favorite things to do. You can look at quantum money. Okay? So here's a building that makes money. Here's money. You could put a quantum state inside the money. How you actually do this, I don't know. But in theory, you could. And then you send it out to people who like money and want to counterfeit it. Okay? The person counterfeiting, if they can't learn what that state is, then they cannot make 2 copies of it. Okay? This is called the no cloning theorem. Okay? And this is physically unforgeable money. It's just not inconvenient. Okay? If you have enough money, you can just copy these things. But physically, you can't. Okay? If there's quantum. Quantum algorithms. So this is Peter Shor. Peter Shor found a way to factor efficiently back in the 90s. And this is the reason a lot of people care about quantum computers, especially from the computer science aspect. What you have here is this is another quantum computer. You put in the factor. Let's say you want to factor some big number. You keep hitting it. It's just going to keep spitting out quantum states. And then what Peter Shor did was found an efficient way to take all these and learn the information inside, and then you get your factor. So this is one way to look at Shor's factoring algorithm. Okay? And of course, factoring is bad because then you can break email, okay, or most modern cryptography. Almost the same algorithm also solves discrete logs, which will break elliptic curve cryptography. So we need to reimagine a lot of cryptography. So here's the quantum states. If Bob wants to learn what he has, you can write this as this optimization problem. Okay? It's a bit messy, so I'm just going to point to it and say, yeah, it's an optimization. So here's the quantum states. Quantum states you can represent as matrices. So that's nice. That's the minimum error of Bob guessing. The dual you can get for free. Or sorry, the dual is not for free. You just write down the dual. You get the solution for free. Okay? So it's a little more complicated, but we can handle it. And now we can start asking questions. What are the shadow prices? Okay? So what if we change one of the quantum states? You change some row to some other row. Okay? Maybe you're in some laboratory and you actually want to change the states for some purpose. And this, for free, you can get the shadow guessing error. Okay? So now you can also change one state, but you can change them all as well. If you have 10 states, you can change each one individually in different directions, and this will give you the shadow guessing error. Okay? So whether this error has high or low shadow price will be good or bad depending on the context. Okay? Whether it's like crypto or algorithms or whatever. How much time do I have? Okay, I can explain entanglement in 5 minutes. So entanglement. So in particular, creating quantum entanglement. So what does this mean? And so you have two particles, electrons, photons, whatever you want. And there's this concept of entanglement. Okay? So usually people draw them really cool diagrams like this, like they're connected by slinkies or string or something like that. The thing is, classically, it doesn't make any sense to think of it that way. Okay? They are connected in some kind of information kind of way. Okay? But we're just going to look at the mathematical properties. And entanglement is at the heart of many or most quantum problems. Okay? So if you take nothing else away from this talk, just know that if you go to a quantum seminar, even if you don't understand anything that's happening, just ask the speaker, what if you add entanglement? Is always a brilliant question. You're like, oh yeah, that's kind of add entanglement. 9 times out of 10 it works. If it doesn't work, just say, oh no, I mean, what if you remove entanglement? One of those will always work, okay? Trust me. So entanglement is just everywhere. You could take almost any problem, just add entanglement, spice it up. Mathematically, what it means is you have a quantum state here, it's a matrix, and you want to write it in this form, as a sum of tensor product of these matrices. Okay? I'm not actually going to work with the definition, but I think it's nice to present. So it's not entangled if you write it like that. So everyone defines entanglement from concerning what it's not. Okay, so it's kind of weird, but. And this problem is NP hard. So I give you the matrix, and I say, is it entangled or not? It's an NP hard problem. So it's tricky. So here's the NP. This is one way to deal with NP hard problems. You can create a sequence of optimization problems. So they're going to look like this. Here's your row. That's the state you want to know whether it's entangled or not. And it's going to give you a sequence of numbers. It's parameterized by this k here. Okay? So I'm sweeping a lot of flavor into this. This is a subspace, but I'm sweeping a lot of information under the rug. Okay? But as you increase k, it's going to get more and more complex. And you can keep solving it and keep getting these values. Okay? So you have a sequence of real numbers. If that sequence stays at 1 the entire time, your state is not entangled. Okay? But if it is entangled, at some point in the sequence, we don't know when, but at some point it's going to dip below 1 and stay there. Okay? So if you have a lot of time on your hands, you can get a pretty good estimate of whether or not it's entangled. Okay? And this is known as a S to P hierarchy. And we can use this sequence of optimization problems to get a handle on the shadow price for entanglement. So the question is, what if we change rho to rho plus t? Okay? We're going to change the state. Are we going to create entanglement? Are we going to remove entanglement? That's what we want to know. So here's our sequence of optimization problems. Here's the dual. Okay? Some nice thing here. And now we can compute the shadow entanglement. Okay? So if you change it to rho plus t, one sec. Oh, there should be a t. I just realized that. But yeah, you have the dual solution, the inner product with that, and the direction you're moving is going to give you the shadow entanglement. Okay? And so far what I've said, they've been kind of application-based, like whether or not you should upgrade a computer or create entanglement. But you can actually start proving analytic properties using these things as well. So the identity is a quantum state. It's not a very good one. So think about uniform probability distribution. Okay, it's not a very good one. But it's an okay distribution. The identity is basically the equivalent to a quantum state. Okay, it doesn't have much flavor to it at all. But if you look at this, it has 0 shadow entanglement. Okay, so identity is not entangled. But if you move in any direction, then you're going to stay, the shadow entanglement is going to be 0. What does that mean? Well, if you're here and you move in any direction, if you're going to stay in the set, that means you're interior. Okay? So you can actually prove the identity is interior to these symmetric extensions, which are like entanglement. Okay? So you can get some kind of convex geometry stuff for free. Okay? And I think I am running out of time. I'll just say what it is. I won't go into any of the details, but you can also look at distance measures between quantum states. So if you have rho and a sigma, how close are they to each other? Okay? Or can I confuse the two? And I'll just say why it's interesting. So if you're in a lab and you're supposed to be creating one state, but your lab equipment is actually creating a different state, that's not good, unless they're close to each other. Okay? Mathematicians care about this because there's norms involved. That's the short answer. Physicists and computer science care about this because there's a lot of applications. Sometimes it's just good enough to look at states that are close to each other. Okay? So I'll end with these functions right here. So this is the fidelity function. So this is, if you're given two states, this is, it's not a distance measure per se, it's more of a similarity distance. Because if they're the same, it gives you 1, not 0. So that's a very nice function. And here's another one. This is called the trace distance. So it's a kind of a normal distance you put on matrices. Okay? And what we can compute is the shadow distance. Okay? Yeah, the shadow distance. So as your states move around, as one state moves in that direction, another state might move in a completely different direction, you can compute how the distances will change as they start moving these directions. Okay? And this is a quick crypto application, but maybe I'll skip that in the interest of time. And maybe I'll summarize in 30 seconds. So just to summarize everything, what I did, I developed this mathematical tool, okay, to give shadow prices. And it has nothing to do with quantum. Okay? You can also use this outside of quantum theory if you want. Right, and this particular kind of optimization is everywhere in quantum. This is just a few pieces. This is just some of my more favorite applications, but like there's a ton of them. They're all over the place. And the shadow prices are given for free. So if you solve the optimization, this will be free information. So it's up to you whether or not you want that information, but if you did want it, it's free. And that's the end of my talk. Thank you.